Far below the surface, silence is never perfect. Even the quietest submarine is surrounded by tiny noises. The creak of metal under pressure, the flow of water along the hull, the soft hum of machinery. Most of that sound is quiet enough to hide inside the ocean's natural hiss. Waves, wind, distant ships, animals, they all create a kind of acoustic fog. But there is one sound a submarine fears more than most. A sound that doesn't just reveal it, but also slowly destroys it. The sound of cavitation. When a propeller turns in water, it does two things at once. It pushes the boat forward, and it changes the pressure in the water that flows over its blades. On the front side of the blade, the water is squeezed and sped up. On the back side, the pressure can drop, sometimes a lot. If that local pressure drops below a certain threshold, something strange happens. The water starts to boil, even though it's cold. Not because the temperature has changed, but because the pressure has. Tiny vapor bubbles form, almost like microscopic pockets of steam. That process is called cavitation. One sentence example. If a propeller blade makes the pressure low enough on its surface, water can suddenly form vapor bubbles there, as if it were boiling cold. At first glance, these bubbles don't look dangerous. They're tiny, they're soft, and they appear in a place that humans rarely ever see. But the real problem is not that they form. The problem is what happens when they collapse. Imagine a small bubble of vapor in the water. When the bubble drifts back into a region of higher pressure, the surrounding water crushes it from all sides. The collapse happens very quickly. The liquid rushes inward, overshoots, and creates a tiny shock wave right next to the surface of the metal. Now multiply that not by 10 or 100, but by millions of bubbles forming and collapsing every second along a spinning propeller. One sentence example. A single collapsing cavitation bubble is harmless, but millions of them hammering against the same metal surface can slowly chew pieces out of it. Cavitation causes three big problems for submarines and ships. It damages the propeller and nearby surfaces. It creates noise across a wide range of frequencies. It can change how the propeller behaves, even reducing thrust and efficiency. For a submarine, all three are bad. But the second one, the noise, is often the most terrifying. To understand when cavitation happens, we need one more concept: pressure versus depth. At the surface, the water pressure is roughly 1 atmosphere, the same as the air above the sea. For every 10 meters you go down, the pressure increases by about 1 more atmosphere. One sentence example. At 100 meters depth, the pressure is roughly 10 times higher than at the surface. This has a direct consequence for cavitation. Near the surface, the ambient pressure is relatively low. It doesn't take much extra suction from a propeller blade to drop the local pressure below the vapor pressure of water. Cavitation can start earlier, at lower speeds. In deeper water, the ambient pressure is much higher. You have to pull the local pressure down much more to reach the same critical point. Cavitation tends to set in only at higher speeds. One sentence example. The same propeller that cavitates easily near the surface might run quietly at the same speed deeper down, simply because the ambient pressure is higher. This leads to a slightly paradoxical situation. Sometimes, a submarine can run faster and quieter at depth than it can near the surface. But there is a second variable we need: speed itself. However, when a propeller spins faster, the water flowing over its blades moves faster too. Faster flow often means lower pressure in certain regions, exactly the condition that encourages cavitation. So two forces are in tension. Depth pushes the cavitation threshold upwards. You can go faster before cavitating. Speed pushes the cavitation threshold downwards. The faster you go, the more likely bubbles form. The safe operating space, where the submarine can move without heavy cavitation, lives somewhere in between. Naval engineers call this idea in practice silent speed. One-sentence example. A commander may choose to stay below a certain knot value, not because the submarine can't go faster, but because any extra speed would make the propeller start to boil and scream into the ocean. In movies, submarines often sprint at high speed while staying magically silent. In reality, the ocean punishes that. Go too fast, and you leave a roaring trail of collapsing bubbles behind you. Engineers use several tools to delay cavitation. First, blade shape. Propeller blades are not flat paddles. They are careful compromises between thrust, efficiency, and cavitation resistance. They may be twisted along their length, thicker near the root and thinner near the tip, and shaped to spread pressure changes more gently over the surface. The goal is to avoid very large local pressure drops in any one spot. Second, diameter and RPM. A larger propeller turning more slowly can often move the same amount of water with less extreme pressure changes than a small propeller spinning very fast. Third, tip design. The tips of the blades are particularly vulnerable. Special tip shapes can reduce vortices and the low-pressure zones that come with them. One-sentence example. Designers might choose a bigger, slower propeller not to go faster, but to go quieter at the same speed. All of this is part of an invisible arms race. Who can move efficiently through water without leaving a loud acoustic footprint? But ship and submarine designers are not the only ones dealing with cavitation. The same physics appears in pumps, turbines, rocket fuel lines, even in the tiny impellers of household devices. Wherever a liquid flows fast and pressures change quickly, cavitation is waiting on the edges. This makes cavitation a kind of universal warning sign. If you see it, or hear it, it means your system is being pushed into a regime where the fluid is no longer behaving in the clean, continuous way your equations assumed. The fluid is literally tearing itself into tiny pockets of vapor and smashing those pockets back together. In engineering terms, that is almost always bad news. One-sentence example. If a pump starts to cavitate, it is often a sign that it's being overdriven, starved of fluid, or operating far outside its intended range. For a submarine trying to stay hidden, cavitation isn't just a signal to the engineers, it's a signal to the enemy. Think back to episode 1. We talked about how sound in the ocean can travel enormous distances, especially at low frequencies. Cavitation produces a broad spectrum of sound. It can include high-frequency hiss and crackle and lower-frequency components that can carry far. Some of it falls right into the bands that sonar systems like to listen in. So when a submarine cavitates heavily, it is not just getting louder. It is speaking in frequencies the ocean tends to carry well, into ears that are specifically trained to hear them. In that sense, cavitation turns the ocean itself into a giant amplifier for your mistakes. This is why commanders and crews obsess over speed, depth, and propeller behavior. It's not just about going fast or slow, it's about how you move through a medium that records and carries almost every mistake you make. Movies often love to show a clean, pinging sonar, and submarines that can jump from silent running to full sprint and back without much consequence. Reality is more constrained. There is no magical drive that lets you cut through the sea at high speed without disturbing it. Every form of propulsion pushes against the water, and the water pushes back, with noise, bubbles, and resistance. In that tension between speed and stealth, cavitation is a constant judge. It tells you very clearly, you are trying to do too much, too fast, in a medium that will tell everyone you are there. By the end of this episode, you can see silent motion differently. You know that a submarine does not just have one speed, slow or fast. It has a silent envelope, combinations of depth and speed where cavitation is unlikely, and combinations where bubbles bloom along the blades and write your presence into the ocean's soundscape. In the next episodes, we will connect this to something else we've already touched: how sonar systems can recognize these patterns, how the ocean's own background noise can hide or reveal them, and how engineers try to design machines that live just below the thresholds where physics itself starts to shout their position into the deep. Silent oceans are never completely silent, but if you understand cavitation, you can at least hear where the silence ends and the danger begins.